Hi, everybody. Dermot O'Shea here, your host of the Antenna podcast. And today I'm delighted to have Professor Satish Sharma from San Diego State University. Professor, would you like to introduce yourself?
Yes. Hi. As Dermot introduced, my name is Satish Sharma. I'm professor at San Diego State University, as well as I'm director of the Antenna and Microwave Lab. And both Dermot and I go together for last 15 years or more when we met first time. So it is great that Dermot we are talking here through this podcast, and I think we have worked together on multiple projects. And Dermot's company has also given gifts to my laboratory to enhance the education of the graduate students. So thanks for that, Dermot.
Yeah, and thank you and San Diego State for your support and for all your some of your great graduates that are here. So maybe, Professor, you can tell us how did you get into the world of antennas and maybe go back to the start. Where did you start your career date, the history, and how you ended up in as a professor in San Diego State?
Thank you. So that's a great question. So growing up in 80s, television was a fancy thing. So if you have to receive television, you have to have Yagi Uda antenna. And if wind is blowing, antenna will move and you lose the signal reception. My younger brother is taller than me. So he used to go fix it. I used to receive good signal. But when I'm going there, since I'm not that tall, I will be rotating and part of the boom, it works. As soon as I leave, it does not work. He used to question me, what kind of engineering you are doing that you cannot fix one thing? And that gave me the curiosity to learn things about it. So when I got opportunity to research, I went into antenna related research as part of my PhD program. And after doing PhD from Indian Institute of Technology, Banaras Hindu University in India, I came as a postdoctoral fellow to University of Manitoba. And then I worked there 2 years before I got to a company called Info Magnetics Technologies Corporation in Winnipeg, Manitoba, as senior antenna engineer. And I was there 6 years researching on different designs for space application to radars, to satellite communication, to smaller antennas like for wireless routers, as well as digital radio broadcast antenna or satellite radio antenna. So that's when up to 6 years, I felt I should go to teaching. So I started applying for faculty positions and I applied three US universities. I got two offers and I like to move to San Diego because my daughters wanted to be California girls. So uh, landed me in California, then South Dakota School of Mines and Technology. So that's how I came. And once I came here, I developed my antenna research portfolio through developing my lab through scratch and hiring students and graduating them, training them, getting equipments. And as I said, support from local industry was always there for me. And not only they hired my students, also they came the support when I needed to test my research antennas so that we can publish papers as well as gift funds. So, this is how I landed here in San Diego State University.
Very good, very good. Yeah, and I think that's the way a lot of. I was born in the 70s and also would have had a lot of experience tuning TV antennas, right? Coat
Yes.
hangers, aerials, trying different ones. And it's funny because today, even on Amazon, there's still huge sales of the very simple TV antennas that allow you to
Mhm.
receive the free to air TV, even in the world of the internet and cable and all that,
Mhm.
there's still a lot of TV antennas sold.
Yes,
So
yes, this is still a booming market.
yeah, and so what would you say, like, so yeah, so you were it sounded like you worked on a similar projects that we do as an antenna engineer for 6 years.
Mhm.
But what's the coolest or most like exciting or memorable antenna project you've worked on?
So that's a very good question. So once I got into University of Manitoba, I started doing LMDS, linked mobile distributed systems, K-band and array antenna design which was the equivalent of today's 5G technology, same frequency, 26.5 to 29.5 gigahertz range. And that was the substitute to communicate between two buildings through antenna link. That's when optical fiber technology was not there. So that was my starting project. Then I got into projects such as the designing for surface wave radar, high frequency surface wave radar antenna, polarimetric radar antenna, space-based radar antenna. Actually, one of the antenna I designed, I have my US patent also for the nose of the aircraft. And when you land or you take off, that's when that antenna becomes very critical. That was for Canadian Defense, DRDC Canada. And then I have US patent, and that was one of the things that excited most because I designed something, which can track the slow-moving objects on the ground from space. And then later on, when I came to Manitoba, from Manitoba to San Diego State University, I have been very, fortunate to have the industry projects through SBIR or STTR from US Defense, as well as some funding from Office of Naval Research and National Science Foundation. I was the NSF Career Awardee. In my department, I was the first one since the history of my department. So, and then that allowed me to perform some unique antenna research. And that included the design for the, earbud antenna that we have here, to a smartwatch antenna, to antenna for the wireless routers, as well as the feed and reflector antenna system, and most recently flat panel phased array antenna, which is the coolest beam steering antenna technology using beamforming ICs through commercial beamforming ICs. And those ones actually last year around October, not only I designed the antenna just for NASA Glenn Research Center, it's a NASA funded project, and then we flew the antenna we designed on 100,000 feet altitude, high altitude balloon. And we had on ground two ground terminals, two mobile ground terminals, and we connected through the antenna payload that we designed, and then we demonstrated 4K video quality, 100 megabits data throughput data and 110 megabits per second data rate, around that, if I'm mistaken the numbers, because it's more than a year thing. So that was the coolest design I did from the most complicated antenna design point of view, which is a phased array antenna. And of course, coming up with the beamforming techniques and the control of the antenna and payload through NASA GRC team. They had all the other instruments to do the ground testing. So it was a collaborative project. So that was the coolest thing, which will still stay with me whole life, because that offered me a great deal of experience beyond antenna design, setting up data throughput testing, and making sure everything really we are using. So that was the coolest thing.
And I know, like, from what I've seen personally, like designing antennas to live 100,000 feet up, we greatly underestimate that, right? Like the effect that has on the antenna design. Maybe you could tell us a little bit more about what can affect the antenna when you're at 100,000 feet compared to on the ground.
That's very good question again. So when you are at 100,000 feet, you are in troposcatter area and tropospheric area, and therefore the pressure and temperature changes, and therefore temperature can, let's say, minus 70 degrees Celsius. And therefore your electronics, beamforming ICs, has to take care of the temperature variation. So many RF electronics may not survive. So we chose substrate material that can survive in space, as well as the electronics that we chose, like beamforming ICs. Then after designing, we did the thermal vacuum testing called TVAC testing at Aerostar facility, who are our balloon provider. So make sure that electronics works. So the main thing that when you go that high in altitude, make sure you have the understanding that your electronics, your antenna has to survive. If not, as temperature changes, relative permittivity of the substrate material changes, and therefore you may get the shift in the antenna performance. And your antenna radiation pattern, if you design for X gigahertz, will not work at X gigahertz, or there's some slightly different frequencies. And every narrowband communication will not be able to establish the communication link. So that's one thing to pay, on which we made a great deal of effort doing ground testing and doing testing in the high altitude balloon environment.
Yeah, yeah, very interesting application though. And then the beam farming, you talked about the beam farming. We've seen, you know, a massive demand for that, or like with the with 5G, with the increased spend in defense and the increased spend in aerospace. Like what's really driving it from your perspective? Have you seen the like the price of the chips come down for beam farming, or the power of the chips? Like what's kind
Yes,
of
so I think when I started this kind of antenna research, 2019, 2018, 2017 time frame, the beam farming IC's prices were, let's say, $250 per chip. Now that technology has given the overall last 7-8 years to almost $30 per chip. So that's the
wow.
reduction in cost because of the growth in the solid state technology and the beam farming IC technology. And therefore, if you want to design the same size of phased array antenna, let's say 16 cross 16, 256 element phased array antenna, then the cost of the production and cost of the prototyping is a lot cheaper than it was in the beginning of 2018, 2017 timeframe. So yes, chip prices has gone down, and it is certainly going to go down in case we are able to implement the 5G technology in full practice. Then the chip prices will go more down because there will be more mass production of these antennas.
Okay. And so I see myself, the need for antennas is increasing, the amount of connectivity that's happening and the amount of antennas per device, etc., the use cases, applications. How about the demand from students? Do you see like more demand of students wanting to study antenna um as theory and as design in the university?
This is very great question again. So since electromagnetics, antenna engineering is more of abstract nature, because it includes Maxwell equations, understanding of electromagnetic wave propagation. So many of the students do not try to take this route. So those who take this route are the really brave one. And those ones can really have the big heart,
Yeah.
to learn these complex topics, and then invest their time in antenna engineering, simulation design, build, prototype testing, and that's for it. Then once you are trained, once you are done, you have a great career. I'm very proud to tell none of my students, those who work in undergrad or masters or PhD or postdoctoral fellow or visiting professors, none of them have any issue with their career. They are the one who are flourishing, and many of them make much more than money I can make as a professor. And I'm very proud to tell that, because they are the one who are in high demand. So this area of engineering is very, very exciting. And I think I must mention, when I visited Tauglas a few weeks back, Tauglas has many resources now. I have seen their anechoic chamber, and with the star system, as well as the many pressure or make sure leaks are not happening. So many things that I saw there. I was so amazed how technology has gone and how Tauglas has cope up with this kind of technology to be ahead of the wireless communication industry. So I see that my students working there, I'm sure they are getting right training, right thing, and they're contributing, and that's why they are working for so many years.
Yeah. No, it's a great area to work in because you get such a variety of projects, and you see the projects happen in the real world, and there's just a huge variety from the smartwatch, as you said, where you have a small, tiny antenna integration, to like large antennas that need to go on base stations or on police vehicles or whatnot. So it's there's a lot of
Mhm.
variety in the projects and use cases.
Yes.
Um, But yeah, here,
Yes.
so here, Professor, on the Antenna podcast, what we like to do is, discuss a technical topic of your choice, and that people can learn from that are interested in the area of antennas. So maybe you could let us know what that is and talk to that. We can also include some materials on the website afterwards if you want to reference them, or that people can follow up and research it later. So maybe you could, give us one of your favorite technical topics and talk to that.
So I think I'll be interested in talking about beam steering antennas or phased array antennas. So a beam steering antenna is the one where you can steer the radiation pattern. Now there are two types of beam steering antennas, two major categories. One can be mechanical beam steering, one can be electronic beam steering. A mechanical beam steering is the one when you design a fixed beam antenna and put it on a gimbal, which is a mechanical motor, and you can point the beam wherever you want. Then electronic beam steering, also known as ESAs, electronic steering antennas, are the one when you steer the beam by changing the progressive phase shifts and that can be part of the beam forming IC, or you can use a stand-alone phase shifter in your array design. So that topic, the reason why I'm bringing it, because it includes not only the understanding of the electromagnetics, understanding of the antenna design, build, also understanding of the RF electronics, and then understanding of the beam forming algorithm, so you can control the pattern in wherever you are trying to steer the beam. So that's a very exciting topic. And of course, I'm the Antenna Propagation Society distinguished lecturer and IEEE fellow of this AP society. So I have experience that I can share with this podcast, and I'm very fortunate to be talking here. So when you design such antennas, first thing you need to choose a rating element, means each of the rating antenna structure. And antenna structure should have a broad beam width. Broad beam width means low gain, low directivity. Rather low directivity, so you have broad beam. Broader the beam, more the scan range you can get. And that sometimes should be cosine theta pattern. And cosine theta means cosine to the power 1 or 1.1 or 0.9 power. Means then you have broad beam and then you steer far. And so that's first consideration. Second consideration, do you want high directivity, or you want more beam scan range? So if you want high directivity, then inter-element spacing is a consideration, which you can choose 0.6 wavelength range, then you can get a bit more directivity, but it will reduce your beam steering. Having said it, if you want to get more beam steering, then you can choose inter-element spacing of 0.45 wavelength, let's say, then you can scan all the way till 70-80 degree, from broadside. And therefore you can see what is your requirement. Are you looking for a more beam steering? Are you looking for more of the directivity point of view? And that's a trade-off the antenna engineers have to make. What is their goal? And then based on how much directivity you want, you choose number of rating elements. If it is 16 cross 16 or 256 element array, you can get something around 29, 28 to 30 dBi of gain, and of course some more directivity based on the aperture efficiency, based on the rating element selection, and also how you are placing the beam forming network or the feed networks. So mostly we are designing phased array antennas, since you have if you are using a conventional approach, then you choose a low noise amplifier. If it is receive antenna design, then you choose digital phase shifter, 6 bit or 8 bit. You also choose the the control for the LNA, how much dB of LNA amplification you want, right? And variable gain amplifier to control the LNA output. Similarly, on the transmit side, you can use the power amplifiers in addition to variable gain amplifier and phase shifter. Now, with the current technology, since beam forming ICs are there, a single IC can take care of both transmit and receive, or only receive, or only transmit. But the beauty is that one chip has everything. Don't have to have discrete components. They are making the beam forming network or power dividers, all in one, and few millimeter by few millimeter chip. And the power handling DC power consumption has to be low, so you don't have to worry about too much of thermal effects. If DC power consumption more means more DC power you have to manage, means more thermal or more heat sinking will be required. So some of those things one has to be careful of what application you are designing for. Is it for SATCOM? It is for the radar purposes, or it is for commercial application, let's say antenna for car or something like that. So one has to be choosing chip properly, which can meet the specification of the frequency, the specification of the DC power consumption, and then on top, how precise beam steering you want. So that means you have to know how many bits of phase shifter you want. 8-bit phase shifter will give you more precise beam steering compared to 6-bit phase shifter. Of course, one can do acquisition and can get even much precise beam steering, but with a narrow beam steering range. So there are ways to deal with that, so that's one thing to do. Then once you have understood these things, that you have to have beam farming, you have to have this, then what environment you are placing it. If you are placing in a space environment, then substrate material has to be space qualified. It has to take care of the temperature variation, pressure changes. Also, its material has to survive, and the electronics has to survive. If it is not in the space qualified case, then don't have to worry too much. But as long as you get the RF performance and DC for consumption, and you have to know how to control the beam farming algorithm. And that's something one has to pay. Again, it can be a very simple MATLAB based beam farming algorithm with LabVIEW or some of the microcontrollers that you can hook to your laptop, and you can write a GUI and see where you want to place the beam. So those are the things has to be done. And then you start modeling and designing it. Of course, the designing the single rating element with the broad beam width with low cross polarization. If you are generating circular polarization, then you still need very low cross polarization, because cross polarization will ruin your axial ratio performance. So that's something to pay attention in the rating element design. Then once you are satisfied with the bandwidth, with the co and cross pole separation performance, then you put in an array fashion. And of course, people do unit cell theory approach to do the flow mode analysis to see that if the active VSWR or active S parameter is still acceptable or not, and then you put in finite array modeling. And there are many softwares these days, full wave analysis tools like ANSYS HFSS, Altair, FICO, and CST Microwave Studio. There are many tools and other tools. If I'm not naming them, not because I have any preference on that, I don't know many tools also. So one can use those full wave analysis tools. With the powerful computers we have, we'll be able to crunch 16x16 array or 8x8 rating based phase array designs. And not only that, you can you also bring if you have the S parameter or the beam farming ICs, then you can do the circuit analysis. You can incorporate the circuit behavior along with the radiation pattern behavior from the antenna aperture, and you can do the post-simulation study. Once you're satisfied, means you have RF electronics effect, then you know there is no loading happening that you don't want, then you can send the file for fabrication prototyping, and after prototyping has happened, RF assembly has happened, then you can do the power testing to see if the board is responding. If not, if there is a ground, it will not respond properly. So one should do power testing. And after power testing is done, then you go back to do the pattern testing in an anechoic chamber, which can be a far field chamber, can be a compact range, or star system chamber like Tau glass hedge. So a chamber that can take care of those frequency measurements. And then you verify the radiation performance by changing the progressive phase shift, or by knowing where the beam should be. Automatically algorithm will calculate and apply that much phase shift. Again, I just said these are beam farming ICs come with both phase shifters, low noise amplifiers if received, and phase shifters, power amplifiers if transmit, and they have RF switch they can toggle. But if you are designing only receive or only transmit, there are beam farming ICs for that also, and they can be dedicated receive or transmit array designs. Only thing, beam farming ICs are not available for all the bands, but starting from X band until Q band, certainly there are chips. And my own lab has designed X band, KU band, K band, multiples of these phased array designs. We name it flat panel phased array antenna designs. We have published papers, and we have research going on, and we have trained many of the students and those who are very capable people.
Wow. That's a lot, right? So just goes to show you need a good antenna designer and partner on your team to help with all that. So yeah, I think there's a lot there, Professor. So it'd be great if you could follow up with some materials. And what's like a lot of people would not be familiar with beam farming and beam steering projects. So what's a common use case? Like where in our everyday lives would we be using a device or application that has beam steering in it?
Mhm, mhm. So think about, if you are trying to, connect a given satellite, let's say low Earth orbit satellite,
Yeah,
then you need if
Starlink
you need
or,
an
or
antenna on ground terminal that can be pointing beam, right? Or if you want to connect a given aircraft or unmanned aerial aircraft system, and you want to keep tracking with the same UAV system, then you have to keep pointing your beam towards that, so
yeah,
that link is built and you can keep doing the data transmission and reception. So that can be one scenario. Of course, if you go to airports, there is one something on ATC or air traffic control, some rotating piece. That's a mechanically rotated tracking antenna they use. So, but the technology with the phase shifter becomes electronic steering. There are some of these cases where certainly but and if 5G technology has gone the way it was proposed back in 2017, 2018 time, where we plan to use these beamforming antennas for the 27.5 to 28.3 gigahertz for the 5G communication. And of course, COVID made some dent on that, and we are not there yet, as far as I understand. But of course, I'm not a very familiar more than what I understand here. So forgive me if my knowledge has some gap there. But then that's where also, had we gone that route, then we had all the cellular phones had 5G antennas, so that as you are moving from base station to base station. As you're driving your car, you are keep connecting, so you don't lose data, and you are having high data throughput because you are operating in higher frequency. Even though today, if your cell phone says 5G, because they are using sub 6 gigahertz band, they are doing uplink and downlink, up convergence, down convergence, so they are still providing you 5G quality signal. But then, had it been all 5G frequency to RF, it could have been much superior, technology. So that could have been another way where we could have grown. Again, forgive me if my knowledge is not complete
no.
somewhere on this.
That's excellent. Yeah, no, very, very interesting. So it goes to show you we're not antennas don't just keep you connected. They're there for safety and helping people be safe as well in all sorts of different scenarios. But that's great. I'll let you get back to your event. Sounds like it could be the cocktail hour there by the sounds of things in the background, or lunch or whatever. So, Professor Satish Sharma, thank you very much.
Thank you. Thanks for having me here. And if needed, certainly please share my email address, sharma@sdsu.edu, and I'll be happy to entertain, and I will be able to provide some basic information, and you can share with your podcast.
Thank you. Thank you, Professor.
Yeah, thanks for having me here, Dermot.
Okay.
And I wish good luck to you and your company and all the great work you guys are doing to meet the customer needs, both wireless industry as well as defense organization. So I wish always good luck.
And you too, Professor. Thanks for all the great work you're doing at San Diego State. So
Thank
have
you.
a good day. Thank you.
Thank you very much. Yeah.